This is Team 1's bar straightness measurement device, sponsored by Autocam Medical. Current manual methods for measuring straightness and roundness are inconsistent and unreliable, leading to undetected defects that cause equipment damage and downtime, with limited data available for quality improvement. So the objective of this project was to design and build a precision measurement system to evaluate the straightness, roundness, diameter, and length of stainless steel rods. Diameters vary from 3.81 mm to 12.7 mm. Lengths include 1.83 meter to 4 meter rods. Additionally, it has the capability to be modified for more lengths and diameters. The first major subsystem for this project is the granite base. The granite base provides a very flat and thermally stable foundation and datum for the rest of the project to be built upon for the most accurate measurement possible. Less variation in the flatness of this datum means that there is a higher degree of confidence in the post-processing calculations for values such as straightness. The second subsystem is the micrometer gantry. The gantry is made up of a couple different components, such as the steel plates, laser micrometer, servo motor, gearbox, and pinion. The gantry is built to be robust in vibration resistance to ensure that the micrometer gets accurate data. The servo motor, gearbox, and pinion gear make up an assembly responsible for meshing with the rack to drive the gantry up and down the length of the rails. The laser micrometer is responsible for collecting data along the bar needed to find values of straightness, roundness, and diameter. During operation, two types of values are being recorded at each interval along the length. The first is the distance that the topmost surface of the bar is from the top edge of the laser micrometer's field of view. The second is the diameter of the bar. The third subsystem is the collet assembly. Its main purpose is to rotate the bar with angular precision to measure different top and bottom surface points of the bar. The collet assembly is placed on a vertically adjustable stage to allow for the height to be changed to accommodate different diameter bars. Because the bars are being rested on their bottom surface, the centerline height will change as a result between the different diameter bars, thus requiring that the chuck can adjust height so as to not induce an initial deflection in the bar. The fourth major subsystem of the measurement device is the rails and V-blocks. The rails are responsible for allowing the gantry to travel smoothly down the length of the bar. The V-blocks, however, are for supporting the length of the bar after the collet. The bar needs to be suspended in the air to allow for the micrometer to see the top and bottom surfaces of the bar. One of the challenges of both of these components was the alignment and top surface flatness of the rails. The V-blocks need to be aligned with a very high accuracy to control and support the bars without inducing any deflections or over-constraints, causing unintentional false readings. And due to the top measurement of the bar being read from the micrometer riding on the rails, the flatness needed to be tightly controlled to minimize false data due to fluctuations in the bearing ride height. The last major subsystem of our project is the electrical panel. The electrical panel is responsible for holding all of the electrical components used in this project. This includes stuff like power supplies, PLCs, IOs, and motor controllers.
Some of the major obstacles that we face as a team throughout the entirety of this project include the lead times of many of our purchased components, especially the granite, which took us nearly 3 months to receive after it was initially ordered. Next is the deflection of our lid, which is shown on the picture on the left. And this was one of our safety features that we initially wanted to have, but eventually had to swap to light curtains due to the deflection of it, which caused it to function improperly. And then finally, we had the deflection of the steel bars that we were measuring. And shown on the picture on the right is some of our hand calculation results and FEA results of these bars sitting in the V-blocks. And this was an initial problem as we had to do many calculations and studies to see where these V-blocks had to be placed so that the deflection of the rods wouldn't affect our final result. Some of the key features for this project include the granite block, which is chosen for its thermal stability and flatness level, the laser micrometer for its measurement capability and accuracy level, the light curtains, which are used for safety reasons to ensure that no injury can be occurred while the machine is on, and finally the HMI touchscreen display, which just allows ease of operation for its users. Shown in this video is a time-lapse of our fully functional laser micrometer machine, which is currently measuring a bar, which you can see, which is laying across the V-blocks. Some of our project highlights include, on the left, a video of when we first had the gantry holding the micrometer moving with our temporary setup. The video in the middle shows the working product on the granite block on the end assembly. And then finally on the picture on the right is the biggest highlight for our team is when the granite arrived to Grand Valley. Shown in this slideshow are the photos showcasing the progress of the granite block when it was first ordered to when it arrived at Grand Valley. Thank you for watching.